Check it out now, y'all.
NanoHub U, online instruction.
Welcome. This is NanoHub U course on principles of electronic nanobiosensors. I am Muhammad Ashraful Alam, a professor of electrical engineering at Purdue University. And over the years, I have actually worked on many topics, many devices, solar cells, biosensors, various electronic components, but of them all, I really have enjoyed working on biosensing. I'll explain why throughout the course. In part because this is a very exciting area with lots of things, interesting things happening. But more importantly, it sort of couples very simple ideas in an elegant fashion. And you will see throughout the course that you really don't have to learn or know a lot to understand things in great depth. So let's get started. So today, you may see that the course title has the word nanobiosensors in it. So I'll start by simply explaining what is a nanobiosensors anyway. So I have a brief outline. I want to distinguish between sensors, biosensors, and nanobiosensors. People often use them almost like as if they are interchangeable, but they are not. And then I'll explain that why do we really care about this nanoscale biosensors. I'll give you a very brief history in 100 years worth of history in a single slide to explain to you where we are and how we have come to this point. And finally, I'll tell you about that there has been a flowering of nanobiosensors, various types of nanobiosensors based on various principles. And I'll explain why there are so many and how people have thought about organizing them before I conclude. Now, if you think about it, all of us interact with the world outside with biosensors or chemical sensors. For example, we have our eyes, hearing, touch, taste, and the sense of smell. And that is how we actually really understand the world outside. But as you can see from the numbers mentioned here, that our sensors are not very sophisticated. And therefore, science didn't really progress until we learned to create artificial sensors that could see something that we personally couldn't, but also expand our range of understanding. For example, although we can only see a very small range of the spectrum, the telescope and the radio telescope allowed us to explore the depth of the universe. On the other side, on small things, the microscope and then electron microscope in early 1900s allowed us to see things that we couldn't see because they were too small. And what I'd like to tell you today is we are going to go towards the bottom. We want to sense things which are small within us. Biosensors essentially allows us to look into things, biomolecules, that are too small to see otherwise. Now, of course, biosensors are everywhere. For example, if you ever have gone to a doctor's office, this old instrument invented in 1800s, stethoscope, thermometer, glucose meters, these are all in some way biosensors. And if you really want it to be very sophisticated, and of course we have this MRI machine, the giant machine where people are wheeled in for extraordinary sensitive detection of various types of anomalies. But these, I wouldn't call them biosensors. Biosensors, or at least nanobiosensors, these are biosensors, but nanobiosensors are even smaller, can detect things at an even lower concentration. Now, why do you care? The reason we care is because our body, or in any human body, is essentially has a hierarchy of structures. We start at the very end, beginning with the DNA. Of course, then there are intercellular process, things that go on within the cell itself. Then there are organs, and then there are a collection of organs. Now, most of the time, when you think about a disease, let's say somebody has a lung cancer or somebody has a prostate cancer, the disease has already manifested in the organs. And in that time, in some way, it's too late. The reason you can detect it so late, we need to wait so long, is because most modern sensors are not sensitive enough to detect any loss of function at much earlier stage. For example, we generally have to wait till concentration reach to the millimolar or a micromolar regime. Wouldn't it be much more beautiful or wonderful if we could detect processes when they go wrong at a much earlier stage, let's say at the femtomolar concentration? So nanobiosensors will allow us to actually detect things at a much earlier stage of disease development. Now, the reason we need such a high sensitivity can be best understood with a Google map. Now, everybody actually has a network, like a road network in the United States or any other country. Now, if you had a very poor resolution Google map, then of course, you'll not be able to go where you need to go. But instead, if you had a high resolution Google map with all the minuscule small roads all clearly defined and highlighted, then of course, we'd be able to go travel anywhere, understand any breakdown of the network in a much more final level. So nanobiosensors will allow us to essentially probe the network which doesn't show up in normal biosensors. And if we are successful, let's say, in that case, one day we might be able to do the circuit diagram of a person, essentially being able to explain every interaction in the whole biochemical network. Now, if you look at a recent blood test, it's one of my recent blood tests. I hope nobody is there's no doctor in, so that nobody is really trying to find if there's anything wrong with me. But the point I wanted to make, that a recent test, next time look at yours, you will see most of the concentrations, like millimolar per liter, millimoles per liter, most of them are relatively high concentrations. But as I mentioned, 2 slides before, that actually if you could detect things at much lower concentration much early on, that would have been actually much better. So let me give you an idea about what type of concentration are we talking about. When we think about a molar concentration, this is really the Avogadro's number of molecules per liter. And if you think about a small box that is 100 micron on the size of maybe a large cancer cell, then we have in a micromolar, we have billion particles. In a picomolar, the same box would contain 1,000, and a femtomolar, just 1. Now, if that analogy is not explicit or the dimension didn't make sense much to you, I just want to explain that a picomolar concentration, if you do an equivalent conversion, it will be as if you dissolved a single molecule of salt in several Olympic-sized pools. That is how low a concentration we are shooting for using nanobiosensors. Now, what type of molecule are we going to think about? Well, we are going to work with a large number of molecules, different types of biomolecules. But the reason we need nanobiosensors, which is nanoscale 10 to the power minus 9 meters, that's nanoscale biosensors, is because most of the biomolecules, whether for glucose for diabetes, which would be about a nanometer or so, to a cancer cell, which would be tens of microns, in that case, all these molecules are relatively small. So when you have something at low concentration and which are themselves very small, the only way to detect them is to marry nanotechnology with biotechnology so that we can have sensors with extraordinary sensitivity which are also of size comparable to the biomolecules themselves. And hence, we need nanobiosensors. Now, you might think that people had been thinking about marrying this nanotechnology or technology, electronics, and biology only recently. That wouldn't be true. In fact, this has been going on for almost 100 years. If you think about it, the beginning of the 19th century, late 18th century, people began to be aware of virus and bacteria. Then, of course, in 1950s, the protein and DNA came along, and we had a better understanding of these molecules. And then polymerase chain reaction, something that I'll explain later on, came along a little bit later. At the same time, of course, the electronic technology also evolved. Vacuum tube happened around the same time, early 1900s, MOSFET and bipolar transistor, mid-1950s, and the integrated circuit, as you know, that have been around for last 40 years. And from very early on the very left, you see that the pH meter essentially allowed vacuum tube to be integrated in measuring the pH or potential of hydrogen of orange juices, and that made Beckman a billionaire. Then came along in 1960s to 1980s these glucose meter, which integrated the technology of creating microelectrodes with ability to sense glucose at a very small scale. And today it is in every shelf in Walmart and other large stores. And then, or finally, today, in fact, the IC technology and biotechnology have combined together to create genome sequencers of extraordinary sensitivity and ability. And in fact, people had been going even further. They had been trying different technologies based on nanowires, droplets, and novel devices. And we'll talk about them all in this course. How far have we come? It's really remarkable journey in terms of biosensing. Even 20 years ago, genome sequencing, the ability to read the DNA using nanobiosensors, was simply non-existent. People need industrial scale systems in order to sequence them. And today, you can sequence them in a tiny chip that has the size of that is of the ICs comparable of the things that you have in the iPhone. And in fact, if you had to compare the corresponding progress, this would be equivalent to 100-year progress in the integrated circuit technology. And in fact, biosensing has come farther in 20 years than computers have come in last 100 years. That's really impressive gain. Let's say then you understand nanobiosensors after taking the course. What good is it going to do you? Well, there are many applications. I'm going to give you a few examples before I wrap up. The first one is personalized medicine. As you know, that our genetic information, the blueprint, is written in our DNA. And the DNA is essentially a long string of molecules that encodes basic program for life. Of course, different organisms have different length of DNA, and this DNA is unique to a person. And so therefore, by reading the DNA of a particular person, we can essentially understand the network associated with this, or the program associated with that person. And therefore, we may be able to design medicine that is specifically good for this or that or this person, specific person. This is the promise of personalized medicine. And the nanobiosensors will help us do this, as we'll see later. What else? Well, the most interesting development of nanotechnologies has been not making of the transistors smaller and smaller. Today, we already have billions of transistors in a single IC. Instead, the most interesting directions have been loading those transistors or complementing them with new technologies like sensors, gyroscopes, biochips and all. And in fact, once again, the promise of nanobiosensors is that it will be able to integrate these nanosensors with mobile devices, allowing one to have complete continuous monitoring of biophysical activity of that person. We can essentially compress a big lab full of people, essentially with a single IC that can do the same job of a lab, and the lab on a chip rather than in a lab in a big medical facility is the promise of nanobiosensors. And finally, even the biomedical instrumentation, that can become much more intelligent, much more sophisticated. In this particular picture, I'm showing you a stent, and the stent is not any normal stent, but rather there are all these sensors, temperature, pressure, and other sensors embedded within the stent itself. And therefore, in these cases, these nanobiosensors, these biosensors make a stent or medical instrument far more intelligent than it was ever before. And in fact, people say that once the wireless and implanted biosensors, many of them at nanoscale, once they come together, the possibilities are limitless. This, therefore, has led to this great flowering of biosensors. What I have shown you is a collection of sensors that have married the nanotechnology, technology of the very small, of the nanoscale, with the biosensing. So there are sensors based on carbon nanotubes, nanosphere sensors, cantilevers of various sort, nanotubes. So people are trying with various combinations, various technologies to create sensors that will be extraordinarily sensitive. And look at these numbers, picomolar, nanomolar, attomolar. And these numbers, as I said, is equivalent to detecting a single grain of salt in 10 Olympic-sized pools within a few minutes. That is a remarkable ability. And so what I'm going to do in this course is essentially going to understand how these sensors function. We'll be using very simple approaches and then gradually peel away the layers of mystery and see how elementally simple most of this function of these sensors are. So let me conclude then. So I have tried to explain that biosensors by itself is not new. It has been around. It's a $100 billion business with more than 1,000 companies. So this is not something that we are inventing per se. However, the nanobiosensors, which essentially uses nanotechnology to enhance biosensing, that is almost just a 10-year or 15-year-old field that did not exist before. And the promise at the end of the day is unprecedented sensitivity and the form factor. By the word form factor, I mean the sensors are so small that they can be implemented, they can be integrated, and therefore allowing a whole set of options. And finally, what I want to explain to you the origin of this sensitivity. Why nanobiosensors are so sensitive is not well understood at all. If you ask 10 people in the field, they will give you perhaps 10 different answers. So one of the great goals, one of the key goals of this course is to explain in a simple way that what is it that is behind this great enhancement of sensitivity of biosensors. What makes biosensors work? So that's it for this. Now, before we move on to the next lecture, let me quickly acknowledge that most of the things that we'll be discussing in this course are based on the work with my graduate students, especially Pradeep Nayar and Jang-Hyun Go, and my colleagues Rashid Bashir and David Gaines, and of course funding from different funding agencies, including National Science Foundation, National Institute of Health, Department of Defense, and network of computational nanotechnology. So this lecture, I just gave you an introduction that why should you care and what is a nanobiosensors. In the next lectures, I'm going to introduce you the actors of this drama, which are the biomolecules and the biosensors themselves. Until next time, take care.